So here's the question. What happens if you mix 16 ounces of cornstarch with about 2 cups of water? Well, you actually get something kind of strange. It's actually a different state of matter from the ones we're used to in chemistry: liquids, solids, and gases. It's something that acts as a transition between a solid and a liquid, and that's called a non-Newtonian fluid. Now, that's all great, but you may be asking, well, what exactly is a non-Newtonian fluid? Well, let's just go back to the beginning. So, in physics class, we were tasked with dropping a ball from around 6 meters into a cup on the ground. The only challenge is the cup was moving on the top of a little electric car moving around 35 centimeters a second. So, after doing some calculations to see how long it would take the ball to fall, and consequently how far the car had to be when we dropped it, we decided to take a shot. And so, after dropping the ball and having the car align while it was falling, it fell into the cup and hit some of the tissue paper and paper we had just stuffed into the cup to try to catch it. However, on the first try, although I had made it in, it bounced out. And so I started thinking of ways you could fix this. You could add more paper and tissues, but that's unreliable and doesn't really solve the problem. You could try to decelerate the ball while it's still traveling, but that's too complicated and it might even make you miss your target in the end. So then I realized someone in my group had suggested using water to catch the ball. And it's true, water decelerates things very quickly. However, there's a couple issues with water. One being that its density is very close to 1 gram per milliliter at room temperature. So, what does that mean? It means if we took the cup and filled it to the top, there's a chance that if we mounted it on top of the car, it would just tip over because of how much it weighed. And so I thought, okay, why don't we just put a small amount of water just in the bottom of the cup? But I don't think that'll be enough to decelerate the ball, and it might just pop right back out. So I thought, okay, what can we put in just a small amount that will be able to decelerate the ball in a short period of time? You may have guessed this already, but what I chose to examine was a non-Newtonian fluid. Now, a non-Newtonian fluid is any heavy molecule that's been suspended in water. The molecule I was using was cornstarch, which has an extremely complex structure that lends it to be very heavy and work perfect for this application. And so, in this solution, you have this heavy starch molecule surrounded by a bunch of water molecules. And whenever a force is applied to the top, it causes the water molecules and this heavy molecule to become more dense. And that area tends to become more like a solid because of that. And you guys already know some non-Newtonian fluids. One of them happens to be ketchup. I'm sure you guys have all seen when ketchup just won't come out of the bottle. Another one is syrup that you might put on your pancakes. Once again, you can see why that would behave like this. And so, theoretically, if I were to put about 1 inch of non-Newtonian fluid in the top or bottom of the cup, the ball should hit the top of the surface, and because of that cascading effect of the molecules slamming into each other, creating more dense regions that become very hard and almost solid, the force should be distributed downwards, then outwards, until there isn't enough force at the bottom for the non-Newtonian fluid to act like a solid. And what this should do is it should give the ball an impact surface so that when it hits the non-Newtonian fluid, it will just sink in instead of bouncing out. And so, when you set up the experiment again, drop the ball into the cup, it shouldn't bounce out. And so I went outside to try this experiment for myself. And so here I have just a sample of the non-Newtonian fluid, same ingredients I said before, just cornstarch, water, and a little blue food dye for effect. And you can see it acts a lot like a liquid when it's not being agitated at all. But when I tap on it, it resists the force completely, and you can kind of see the ripple effect that it has as the surface tension of the liquid just completely repels all the force I can add to it. As you can see, my hand's pretty dry because I'm not actually getting to the bottom of the container. I'm not getting to the liquid at all. So what I'm going to do is I'm going to drop a couple marbles from about a meter. And by drop, I mean throw, because the balls we were using in the experiment were traveling a lot faster than if I just drop it at a meter. So I'm going to toss them straight into the container, and I have 3 sized balls, each one to represent a different impact force in the experiment. I have one larger one, and all the balls have different masses, the largest being the heaviest, as you would expect. And so what I'm going to do is I'm first going to just show you zoomed out what each one does in the liquid, first being the big ball. And you can kind of see it there, what just happened, but you can see that it did not bounce out of the container, even though I only have about an inch of Newtonian fluid in there. Now I'm going to do the same with the medium-sized ball. Just toss it in. And you can see once again it didn't bounce out, and it also tends to sink into the surface once it lost its momentum, and it's no longer imparting a force to the liquid. The Newtonian fluid doesn't act like a solid. So here's the last ball, the smallest one, and you might not have even been able to see that. That's how fast it went into the fluid. So now I'm going to show you a little zoomed in slow-mo view of each one again. Now here's the big ball, and you can see that made a sort of crater in the fluid before bouncing up, landing here, and you can see it's rolling around on the surface because the surface is still acting like a solid, but now it's going to sink in, obviously, and I'm going to have to pick it up and clean it off. And so the next one I'm going to show you is the medium-sized ball in slow motion. Now that one didn't bounce at all, but you can see it still stayed on the surface for a good amount of time before it sunk down. And there's the small one, and you can see that had almost zero ripple effect. Now, just for fun, I threw a hammer against the liquid just to see what it did. And you can see here in the slow motion that when it hit the surface, it actually bounced. And this bounce was not very high even, and I think that's pretty conclusive that, and even though you can impart a huge force to this fluid, it's never really going to bounce out of the container.